All right, this is AP, AB, and BC Calculus. We're doing Unit 2, Section 1, which is defining average and instantaneous rates of change at a point. So we're going to start by talking about stuff that you can do without calculus, which would be things like average rate of change, and we're going to work our way towards instantaneous rate of change, which is going to use limits and therefore calculus. All right, so the average rate of change of a function is basically old school slope, right? Change in y over change in x, or y2 minus y1 over x2 minus x1. If you have a function on the window from a to b, it would be f of b, which would be the second y value, minus f of a, which would be the first y value, and then b minus a, which would be x2 minus x1. So the same thing that we have up here, right? If I wanted to talk about the average rate of change between some x that I start with and then some x that is h units away, so x and x plus h, I could use f of x plus h, which would be the second y value, minus f of x, which would be the first y value, over the quantity x plus h minus x, which would be the second x value minus the first x value. Or if I simplify that, I'll just end up with an h on the bottom. This thing right here is generally called the difference quotient. So remember, names in math are super specific. They're either named after a person or they're usually named after what something does, right? This is called the difference quotient because it has a difference, right? So see the difference, right? And it has a quotient, right? Look at the division, right? Difference quotient. But specifically the difference quotient, when you refer to the one that's important, this is the big one, that's the one they're referring to. Lots of things are differences and quotients. This is the difference quotient. It's a big deal. All right. So let's go ahead and start with example 1. We're going to find the average rate of change of the function on the given interval. So in order to do this, right, I'm going to need to find f of pi over 18, right, which is going to be the sine of a 3 pi over 18, which is the same as a pi over 6, which, because we know our unit circle, we know is 1/2, right? I'm also going to need to find f of 0, but that's just the sine of 0, which is totally 0, right? So now my average rate of change, right, so my average rate of change, because I'm lazy, is going to be y minus the y value over my x minus the x value. So I'm going to get 1/2 divided by a pi over 18, but nobody's ever going to be okay with us leaving an answer like that. So that's going to be a 1/2 times an 18 over pi, right? So I probably leave my answer as a 9 over pi. Cool. For P1, try the same thing. You're going to find the average rate of change of this function on this interval. So again, you're going to need to find the two f values, and it doesn't really matter what order you find them in. Just like when you find slope, it doesn't actually matter which y value is y1 and which one's y2. So this is going to give me the tangent of 2 pi over 8, which is the same as pi over 4. Because we know our unit circle, hopefully we know that's 1. I probably should have drawn this on the last one too. This is where pi over 4 is. The sine and cosine values are the same, thus their ratio of sine over cosine is a 1. And over here, if we had drawn this, this is where the sine of pi over 6 is, and it's a y value of 1/2. So again, really helpful that you know the unit circle, right? Because you're sometimes going to have to do it. So tangent of 0 is sine of 0 over cosine of 0, which is 0 over 1 or 0, right? So that means that my average rate of change is going to be y minus the y value over my x minus my x value. So I seem to get a 1 over a pi over 8. When I flip the denominator, right, to multiply by its reciprocal, I end up with an 8 over pi. All right, moving on. Cool. So in E2, we're going to find the average rate of change of the function on the given interval. Again, same basic deal, just giving you a slightly different function. So we're going to do f of 5, which is going to be 25 plus 15 minus 4. That should be a 36. And we're going to do f of 1, which should be 1 plus 3 minus 4, which is a 0, right? So my average rate of change should be y minus the y value over x minus the x value, which seems to be a 36 over 4 or a 9. We go on to a P2, same idea. So my f of 2 is going to be a 2 times an 8, so that's a 16, minus a 10, so that's a 6. My f of negative 1 should be a 2 times a negative 1, so that's a negative 2, plus a 5, so that's a 3, which means that my average rate of change should be 6 minus 3 over 2 minus a negative 1, which is 3 over 3 or 1. Cool. All right, so now we're going to be given a table, and we're going to find the average rate of change on the window from -2, which is here, to 3, which is here. So in this situation, I'm handed this table, and they've done most of the work for me, right? My average rate of change should just be f of 3 minus f of -2 over 3 minus a -2. Well, those are numbers I was given, right? I was given f of 3 is an 8. I was given f of -2 is a 10. So 8 minus 10 over a 5 gives me a -2/5. So just because information is presented differently doesn't mean you should stress out. Most of the time it's actually being handed to you in an easier way. Go ahead and try a P3. It's the same idea. As always, you can pause me if you want. So the average rate of change from here to here, right? So my average rate of change is going to be f of 7 minus f of 1 over 7 minus 1, right? That's going to be a 2 minus a -3 over a 6. So that ends up being a 5, 6. Cool. All right, so now let's go ahead and do some stuff that has word problems, because that's just good for you. Example 4. The table below gives Fletch's velocity as he rides on his balance bike in feet per second. Recall that acceleration is the rate of change of velocity and will thus be measured in feet per second squared, or feet per second. Sorry, there's an extra parenthesis that's missing here, and that's just going to bother me. Okay, so we have time in seconds. We have f of t, which is his velocity, right? So this is velocity. Notice it's positive because he's only moving in one direction, although he really does like to go backwards and go beep, 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 because he's 2, and he thinks it's awesome. All right, so we're going to use the table to approximate Fletch's acceleration, which would be the rate of change of the velocity, right? So rate of change of the velocity at 3 seconds. You'll notice that 3 doesn't appear on the table, but 2 and 4 do appear on the table, and it said approximate, right? So his acceleration at t equals 3 is going to be approximately y minus the y value, so 1 minus 3 over, and actually let me just add, let me make it a little clearer what I mean by this, right? So it would be f of 4 minus f of 2 over the 4 minus 2, right? So that's where I was getting the 1 minus 3 over 4 minus 2, right? So it's a -2 over a 2, or a -1 foot per second squared. So why is it negative? What does that mean? Well, that means that he's slowing down, right? Like he's pushing his balance bike forward, and he's still moving forward. He's not making his backwards beep, beep, beep. He's moving forward, but he's slowing down, probably by dragging his poor overburdened shoes on the ground. Okay. Next one, B, use the table to approximate his velocity, or I'm sorry, his acceleration rather, at 10 seconds. Well, again, we don't have 10, but we do have 9 and 12, so they would be the logical choice. So to approximate his acceleration at t equals 10, right, I'm going to approximate that by using his velocity at 12 minus his velocity at 9, because those are the two times that surround 10 seconds, right? Over 12 minus 9. Sometimes my brain doesn't work properly. Okay, cool. So that's going to be a 3 minus a 2 over a 3. So we get 1/3 foot per second squared. And there we go. And again, that means that he's now speeding up a little, right? He's still moving forward, but he has started pushing and moving faster. Notice that when you have a problem where units are given to you, you need to make sure that you have correct units in your answer, right? Don't make up units. Don't be like, hey, it's second squared because I said so. No, if there's seconds in a problem and you know that the answer should involve second squared, make sure that you have appropriate units. But please don't add units when they don't already exist in the problem. All right, P4. Pause me if you want to do it on your own. So the table below gives Bailey's velocity as he meanders on his afternoon walk in feet per second. So this is Bailey. He's my very old lab husky mix. He's a good boy. Recall that the acceleration is the rate of change of velocity, and thus would be measured in feet per second squared. Again, forgot that pesky parenthesis. It's going to drive me nuts. So we're going to use this table to approximate Bailey's acceleration at 2 seconds. So again, you'll see that 2 doesn't show up on the table, but they didn't ask for the exact velocity, the exact acceleration, which we're going to learn how to find. What they asked for was the approximate acceleration. So his acceleration at t equals 2 is going to be approximately Bailey's position, or Bailey's velocity at 3 minus Bailey's velocity at 0 over 3 minus 0. So that's going to be a 4 minus 1 over 3 minus 0, which is a 3 over 3, or 1 foot per second squared. Meaning, it's early in the walk, he's accelerating, he's moving faster, he's got lots of energy, even though he's an old dog. Then we're supposed to do the same thing at 5 seconds, right? So there is no 5 on the table for seconds, right? But there's a 4 and an 8, so 5 falls between them. So to find his acceleration at t equals 5, we're going to go ahead and use the 4 and the 8 points, right? So it's going to be Bailey's velocity at 8 minus Bailey's velocity at 4 over 8 minus 4, right? So that's going to be a 1 minus 2 over a 4, which is a negative 1/4 foot per second squared. Why is it negative? Well, because he's slowing down, right? So Bailey, good dog that he is, ran charging out the door super fast to go on his meandering walk and then got really tired and started walking a little slower. Okay. All right, so let's talk instantaneous rate of change versus average rate of change. So instantaneous rate of change requires calculus because it's not over a time interval. If you go back to all of these, right, this average relied on using a time interval, right? So this average here, time interval, time interval. If we go back here, time interval, right? Time interval. There was a window of time. Well, the problem is that if you don't have a time interval, then you're dividing by 0 in the denominator, which you're not supposed to do, right? So you can't divide by 0 in the denominator, so we need calculus. We need the concept of a limit in order to find instantaneous rate of change. So the instantaneous rate of change of f of x at some a, right, is the limit as, so here's the idea, right? And we've seen this in the very first slide probably of this entire calculus class, right? So we have 2 points, we have some curve f of x, right? So if I make a line between these 2 points, that's called a secant line, right? But if I wanted to make a line just at the 1 point right here, that tangent line, what I'd have to do is I'd have to make h really, really, really small, right? Because the smaller I make h, the closer this second point moves over until it's right on top of this point and it functions like it's a single point. Well, we can't actually divide by 0, but we can use the limit as h approaches 0. The other way that you'll sometimes see this written is instead of using the points as a and a plus h, you'll sometimes see this where we have some point A, we have some other point X, and X is approaching A, meaning X is getting moved closer and closer to A until it's a single point the same way as it was above. So notice that this is the same difference quotient that we've seen. The only thing about it is that it now has a limit as that denominator is going to approach 0. So if there's an H in the denominator, right, you'll see it's the limit as h approaches 0. If the denominator is the difference between x and some other numerical value, it's x approaching that value. But the issue here is that we're not allowed to divide by 0, so we need to use limits to find the instantaneous rate of change. Now the notation that we use for that instantaneous rate of change is this f prime notation, right? So when we read this, right, if you were to see f prime, let's say this would be read as f prime of x. And we're going to spend more time talking about that later. So this one right here is f prime of a, this is f prime of a, and we're going to spend more time on that for pretty much the first half of this calculus course. So, all right, let's find the instantaneous rate of change. So we have this formula here, right? We can either use this formula or you can use this formula. I don't care which one you pick. In fact, let me drag both of them in so that we can see it doesn't really matter which one you use, right? So you can either use the one I have right there, or you can use this one, right? It doesn't matter which one you pick. They do the same thing. And I think originally my intent was to show you at least one of the two ways, if not both. Okay, so let's say that we decide to use, let's use this one first, okay? So let's use this one first. Let's use this one second, just to show you how it works. And then honestly, in a real problem, you'd pick, right? So you would choose, and actually, I'm gonna be really honest with you and say that in about 2 more videos, you're not gonna use this method to find this value anyway. So let's say I choose method 1 first, right? So what I'm looking at is I want f prime of 5, and what that's gonna be is it's gonna be the limit as x approaches 5, right? As x approaches that a value, right? Of f of x, which is just x squared plus 3x plus 1, minus f of 5, right? Well, f of 5, if I plug in to get f of 5, that's going to be a 25, right? Plus a 15, plus a 1, right? So that should be a 41, all over an x minus 5. So that's going to be, if we clean up a little bit, and you could try plugging in right now, but if you tried plugging in 5, you're going to get 41 minus 41 on the top, and you're going to get 0, you're going to get 5 minus 5 on the bottom. So you're going to get 0 over 0. So we're going to clean up the top a little. If I plug in, if I clean this up, I'm going to get x squared plus 3x minus a 40. Well, that's useful because 40 definitely factors into a 5 times an 8, and if one of those is negative and one of those is positive, I can get this x squared plus 3x minus 40. I can even tell which one should come out negative because I know that this thing right here is a problem. So I'm pretty certain that one of the factors on the top is going to be an x minus 5 and that that's going to take care of my problem. You can double check by foiling, but sure enough, you end up with an x minus 5 on the top and the bottom. They cancel and you're now clear to plug in. You're going to get 5 plus 8, which is 13. So the instantaneous rate of change, f prime of 5, is 13. Now, I can walk through the other way with the f of x plus, f of a plus h rather, minus f of a all over h, and that's a limit as well. I will say that you're going to find this more tedious. This is definitely faster. Both of the two ways work fine, right? So what I'm going to do is I'm actually going to insert, let's insert a blank page. Nah, I lied. Let's just erase this. So we know the answer we should be getting is 13, right? So if you want to do it the second way, just to show you how you would, and again, if I were you, I would do the first one. I think the first one is much easier, right? So if you chose to do it the second way, right? The second way to find f prime of 5, you would do the limit as h approaches 0 of f of 5 plus h minus f of 5 all over an h, right? So here's why that's not super fun. What this is going to look like, sorry, that's an h approaching 0, is f of 5 plus h means anywhere you see an x, you plug in a 5 plus h. So you're going to get 5 plus h quantity squared plus 3, 5 plus h plus 1. So that's f of 5 plus h. And then minus, in parentheses, f of 5, which we've already plugged in and found that f of 5 was a 41, right? We did that already in the last one, right? So that's my f of 5, okay? All over an h. Well, now I'm going to have to FOIL this thing out. It's not going to be super fun. I have to distribute the 3. And what's going to happen if I do all of this, the limit as h approaches 0, I'm going to get 25 plus 10h plus h squared, first, outer, inner, last, plus 15 plus 3h plus 1 minus 41. Now, what's going to happen when I add up all my terms that don't have an h, which is this, and this, and this, and the negative 41, they're all going to sum to 0, conveniently. Because I have a 25 and a 15, that adds to 40, plus 1, that's a 41, and then I subtract. So now I'm going to get that this is the limit, as h approaches 0, of an h squared plus a 10h plus, oh, sorry, plus a 13h. I missed this guy right here. And that's it, right? And then all over an h. So that's the limit as h approaches 0. If I factor an h out, I can take out one of the h's and I would be left with h plus 13. Well, now when I plug in, that's 0 plus 13, which gives me the same answer that f prime of 5 is 13. But I think that was a lot more work. So again, the average rate of change would be old school slope. The instantaneous rate of change uses this limit process, and we're going to learn shortly that that's called differentiation. So we're going to go ahead and try a P5. I'll be honest, if I were you, I would try P5 this way, but you can certainly try it either way. In the long run, you won't be using this particular method exactly as it is to find instantaneous rate of change. You're going to learn a whole set of much faster options that are essentially short rules that we memorize to skip to the end of this limit process. The limit process can be kind of tedious. All right, so go ahead and try P5. Again, I would suggest that you use this one. You're welcome to use the other one if you want. All right, so I want f prime of 2, right? That's going to be the limit as x approaches 2 of f of x minus f of 2 over x minus 2. Right? So I need f of 2. Well, when I want f of 2, I'm going to plug a 2 in right here, right? So I'm going to get 2 times 4, right? So that gives me an 8 minus a 5 times 2. So it's 8 minus 10, which is a negative 2. So I'm going to get that this is the limit as x approaches 2 of 2x squared minus 5x minus a negative 2 all over an x minus 2. So when I plug in, I'm going to find pretty quickly that, sure enough, the top and bottom both become 0, right? And that's never the answer. Remember, 0 over 0 is never the answer. So this 2x squared minus 5x plus 2 is going to factor, and it's going to factor into something that involves this x minus 2. So when I factor, and again, I don't care how you factor, I just care that you factor right, I recognize that it's a 2x and an x, and I can make the educated guess that this x1 has to be an x minus 2 because it's going to cancel with this guy on the bottom. Sure enough, that totally fits, because if I put a 1 here, when I FOIL to check, I get 2x squared. Outer is a negative 4x, inner is a negative 1x. That's my negative 5x, and my last is a plus 2. These guys cancel, and when I plug in, I get 2 times 2 minus 1, which means my answer is 3. So my instantaneous rate of change in this problem, f prime of 2, is a 3. You could also do it using the x plus h or the a plus h formula that I gave you on this page if you want to do this one. I just think it's a little bit more difficult, but certainly either of them are fine. That is it for topic 1.